Hello 8th graders, we're starting in on the topic of gravity today. Gravity is a type of acceleration is the title of this, and it's something that I'm going to say a whole bunch because oftentimes people think that gravity is a force, and you've heard that probably, the force of gravity. But gravity is actually an acceleration that causes things to have a force. If that sounds complicated, don't worry, that's what we're going to be spending time learning about, and you'll be experts by the end. Before you start this lesson, I need you to make sure that you have done the warm-up first. The warm-up is a Google form that you're going to fill out. It's in Google Classroom, so if you haven't done that, please pause and go take care of that first. You'll also need your notebook with your note side and your practice side too. Today we have 3 jobs to do, and each one of them kind of leads into the next. So the first job is to be able to explain the difference between these two ideas, mass and weight. We've been using mass a whole bunch with our physics units so far, so hopefully you have sort of an idea of what that is. And I know you've heard of weight before, but I bet that you haven't fully understood what it means, especially when it comes to mass. Once we've talked through that, then we're going to talk about how to determine the velocity and displacement for objects in a free fall. So we've done velocity and displacement before. The only thing that we're doing that's different is we're talking about things that are falling. Hopefully this will feel really familiar because the equation is exactly the same as what you've already practiced. We're just adding gravity into the idea. Then the last thing that we have to do is describe gravity using free body diagrams and Newton's second law. So again, this is another idea that we've already played with, the idea of free body diagrams and Newton's second law. The only thing that we're adding is the idea of gravity. So this whole lesson today is taking some stuff that we've already talked about and adding in the concept of gravity to see how it plays a role. So your warm-up today was about this video that you watched, and it was very super dramatic. I hope you enjoyed it. Well, what they did was they dropped a bowling ball and some big ostrich feathers, and as you probably expected, the ostrich feathers fluttered to the ground and the bowling ball went racing straight to the ground. But then they pumped out all the air. And this is where sometimes people make a wrong prediction. Maybe you did, maybe you didn't. But what's happening is those two objects, the feathers and the bowling ball, they get dropped without any air to get in the way, just empty space. And what you hopefully saw was that those two objects, this is a picture, a screen capture from the very end, right before they're about to hit, those two objects, they fell at the same speed. So if you pump out all the air, they fall at the same speed. And the reason why this is really important for this lesson is because I want you to start this lesson with a realization that gravity does not make things fall at different rates. In fact, the opposite. Gravity is a constant thing. It affects everything in a very similar way. So let's talk about that. Over on your note side, you're going to be very busy today, so you probably will need more than one page, so prepare yourself for that. But we're going to take breaks as we go too. So the first thing that we have to say is something I've already told you. Gravity is not a force. So gravity is actually a type of acceleration. So if you're remembering back to Newton's second law, which we'll talk about in just a second, it's F equals ma. Gravity is a type of the acceleration, the A part of the equation. And the next part of your notes is the next line, gravity causes things with mass to have a force. And that one sounds a little bit abstract, so let's pop that Newton's second law equation up there and let's talk about the parts and make sure that we've got it. So gravity is the A part of the equation. And gravity causes anything with a mass, that's the pink, it causes it to have a force. So think about that. If you have some object, as long as it has mass and it's being affected by gravity, it has a force. I can feel my phone pressing down on my hand, and that force that I feel is because gravity caused a mass to push down. So if you were to take this same object that has mass and remove gravity, make gravity 0, now all of a sudden it won't have a force. So imagine going way out into the deep parts of space and you brought my phone with you and you just tried to set it on your hand, you would not feel it pressing down on your hand because there's no more acceleration of gravity. And if there's no gravity, there's no force. In your notes, I want you to add a picture to hopefully help you remind you of this. So imagine a big heavy object that I've put a pink label on for mass and a label pointing down. So there's a force that's pointing down, and that's what we call weight. Weight is actually a force that's caused by gravity. So we can rewrite Newton's second law, and I want you to add this to your notes. We're going to use this equation a lot. But it's not a different equation. It's actually Newton's second law, just rewritten. Look at the colors. So if you have some object with mass, and it's affected by gravity, gravity is a type of acceleration, so m times a, it causes a weight, and weight is a type of force. So you sitting in your chair, you have mass, you're being affected by gravity, and that's why you have a weight. Same as all the other objects that might be around you. And the reason why they have different weights is because they have different masses. It's not because gravity is different. However, if you went to a different planet, then gravity would be different, but we're going to tackle that in a different lesson. So the next part of your notes I want you to add is the acceleration of gravity. So on Earth, the acceleration of gravity is actually 9.8 something. You could easily Google search it and look it up. But for the purposes of this class, I am not going to be super picky about that precision, that level of precision with that number. Since it's so close to 10, 9.8 rounds up to 10, and I want you to get the practice of understanding the concepts more than using the actual number, we're going to use the number 10 in this class. Plus, it's really nice to do math with the number 10 as opposed to the number 9.8. I can do a lot more things in my head with the number 10. So in your notes, make sure that you have that Earth's gravity's acceleration, the A part, is 10. So that's this part in the equation of F equals ma. So when we're ever talking about weight or gravity pulling things down, the A is always 10. So let's go back to the bowling ball and the feather for just a second, and let's talk about why those two things fell at the same rate. So let's say that you wanted to solve for the acceleration. And so you rearranged the equation so that you're solving for A. Remember, if you cover A in this triangle, you'll get F over M. I just rearranged the equation. Well, think about a bowling ball. A bowling ball has a really big mass, so I made the M in this equation really big. And because it has a really big mass, gravity is going to cause it to have a really big force. And you could feel that too. If you put your hand under a bowling ball, you're going to feel the bowling ball press down on your hand really hard. But the key thing here is that the acceleration of gravity, is just a constant number. It's still 10. So let's put in some actual numbers. Let's say that the bowling ball has a mass of 50. That would mean that it's pressing down on your hand with 500 newtons. But gravity is always 10. Check the math. 500 divided by 50 equals 10. Well, let's go over to the feather. So you hopefully know that the feather has a really tiny mass. And because it has a tiny mass, gravity is not going to cause it to push down nearly as hard. But it's experiencing the same gravity that the bowling ball was. Notice that the A, I made them both the same size for both the bowling ball and the feather. The difference is that the feather has a little force and a little mass. Let's put some actual numbers here so that you can see this. Let's say that the feather has a mass of 1 kilogram. That would actually be a really heavy feather, but I wanted a nice easy number. It's obviously much smaller than 50. So if the feather had a mass of 1 kilogram, that would mean that gravity would cause it to press down with a force of 10 newtons, much smaller than the bowling ball. But notice the acceleration of gravity is still 10 for both the bowling ball and the feather. So they're both experiencing the same acceleration of gravity, but the results are different. And to me, this is one of the most amazing things of the universe. Think about how cool that is. This law of the universe, this idea of gravity, causes everything around us, no matter if it's a house, a pebble, a speck of dust, whatever it is, it doesn't matter. Gravity knows how to pull on those things with the exact right amount of force so that they all accelerate the same way. So let's check your understanding really quickly. I have these two questions up on the screen. You don't have to write anything for this one, but I want you to think about the answer as we go, and I'll pause and give you a chance to think. So here's the first one. Does gravity pull on all things with the same force or different forces? In other words, which of those pictures above is the right picture if it were a force diagram? Take a second and think about that. And then the next one, gravity causes the same acceleration for all things. So let's check. So gravity does not pull on things with the same force. You can prove that to yourself by putting something that's really small into your hand and something that's really big into your hand, and you'll feel them pressing on you with different forces. Gravity causes everything around you to push down with all sorts of different forces. But they're all coming down with the same acceleration. So the correct force diagram is not this one. Everything experiences different forces. So the feather is going to press down just a little, but the bowling ball is going to press down a lot. But the thing is, they're going to accelerate at the same rate. For this first objective, we have just two things left to do. So still over on your note side, make sure that you have Newton's second law, and let's make sure that we're defining each letter in this equation to talk about weight. So the force, when we're talking about weight, is this word called weight. It's how hard something is pressing down due to gravity. This is a definition that you should have added to your notes. For mass, the definition for mass is how much stuff something is made of. We did chemistry last quarter, and it's literally how many protons and neutrons are in something. Mass is not the same as weight. Mass is how much stuff. Weight is how hard that stuff is pressing down. The A in the equation is the acceleration. It's the reason why weight exists. So it's how quickly it speeds up when dropped. So if you take a certain amount of mass, if it's experiencing acceleration, it will have a weight. So all three of these things go together, and that's why Newton's second law was such a big deal, is nobody had ever put these three things together mathematically before, and Newton was the first one to do it. So it also says here that acceleration is different on every planet. For now, just know that it's a different number. On this planet, it's 10. And on every planet, it's different. And we're going to talk about why in the next lesson. But for now, just know that it's different. So if we rewrite that equation, weight equals mass times the acceleration of gravity. Please notice that this is the exact same equation. Both boxes in yellow, they're the same. We've just given different words for a different occasion. So over on your practice side now, I need you to do this quick right. Use the vocabulary weight, mass, and acceleration to explain why the bowling ball and the feather hit the ground at the same time in the video when they pumped out all the air. Pause this video and answer that now. One more on your practice side, now that you've answered about the feather and the bowling ball. Think about a space person way out in space. Why do we call things weightless up in space? And I've left the equation on the screen to help you think about the answer to that. So one more on your practice side. Describe why do we call things weightless? Try using the vocabulary words gravity and mass in your answer. We've made it through the first of our three objectives. Hopefully at this point you're able to explain the difference between mass and weight. You've done a lot of writing. If you need to take a little break, you should pause this video, go take a walk, do some stretches, take a short break, and come back to me when you're ready for number 2 on our objectives list. If you're still watching, you've taken a little break. Now we're going to talk about how to determine the velocity and displacement for an object in free fall. So this again is using an equation that we've already used in the past. We've done displacement and velocity. What we're only changing this time is talking about how something is falling. Instead of a car driving down the road, we're talking about some object falling towards the earth. Just change the direction. So since it's the same stuff, let's make sure that we have the same equation as before. So when we did acceleration in the first lesson of this unit, I showed you that acceleration equals change in velocity over change in time. Please make sure that you have this equation again over on your notes side. Let's identify again that the acceleration part, the A, if we're talking about things falling on Earth, the A part is always going to be 10. So we can rewrite the equation to look like this. 10 equals change in velocity over change in time. And now we can figure out how fast things are going to be going if we drop them for different amounts of time, because we know the acceleration of gravity. We could also use the equation in the form of a triangle again. Just remember that the A is always 10. So what we're going to do to practice is we're going to pretend like we just took Justin Bieber and we pushed him off a cliff. So on your note side, I need you to make a little sketch of a cliff and a little sketch of our Justin Bieber, and he's going to get pushed off the cliff. And what we're going to do is we're going to calculate how fast he's going, how far he has fallen, and his acceleration at 3 different seconds along the way in order to practice using this equation. So we've got time 0, time 1, 2, and 3 as he falls down the cliff. So pause and add this little sketch to your notes. The equation we're going to be using is the same, the change in velocity with the acceleration in time. So I have the triangle here because I find that to be most useful. And remember, the acceleration is 10. For honors students, You're going to be responsible for being able to calculate the distance that something has fallen. For regular class, that's actually not an 8th grade standard, so it's not something that you have to do. However, if you find it interesting or if you want to push yourself, I encourage you to use this equation as well to find distance, but it's not technically part of our required learning objectives for this topic. So let's start. At time 0, as Justin was just pushed over the edge of the cliff, think about what his acceleration would be. I hope that you're sitting there going, wait, Nelson said that the acceleration was 10, because that's gravity on Earth. And that's right, it's going to be 10 meters per second per second. Even though he hasn't really started going anywhere just yet, gravity is causing him to accelerate at 10 meters per second as long as he's on Earth. Because he hasn't had any chance to fall yet, he has only been falling for 0 seconds, his velocity right now is going to be 0, and he hasn't gone anywhere. So 0 for his distance also. So the time 0 is a pretty easy one. Let's think about 1 second later. 1 second later, think about this. Did the acceleration of gravity change? Hopefully you're saying no, he's still on Earth, so the acceleration of gravity should still be 10. And if you said that, good job. 10 meters per second because he's still on Earth. For velocity though, now that he's been falling for a whole second, we have to figure out how fast he's going. We can go the long way, we can use the equation and figure out what his change in velocity was and plug in the numbers. But if you understand what acceleration is, it actually is a little bit easier. Acceleration is a change in velocity. So it means that he's adding 10 to his velocity every second. He's adding 10 meters per second every second. So if he's been falling for 1 and he's adding 10 every second, now he's going 10 meters per second. If you plug that information into this distance equation, pause the video if you want to give that a shot on your own. Make sure that you're doing the square first. When you do that, you'll find out that he had fallen for a distance about 5 meters. Let's go to second 2. The acceleration at second 2, because he's still on Earth, think about what that should be. Hopefully you still said 10 meters per second because he hasn't gone to a new planet. Gravity on Earth does not change. His velocity, though, is a little different. So he's now been falling for 2 seconds, adding 10 meters per second each one of those seconds. So now he's up to 20. And calculating for his distance, pause if you want to do that on your own. His distance is now 20 meters. By the time we get to 3 seconds, his acceleration has not changed, still going 10 meters per second, but his velocity is now up to 30 meters per second because he's been falling for 3 whole seconds, and he's fallen a whole distance of 45 meters. If you need to pause and go back and review any of this, do that now, but I need you over on your practice side next. And on your practice side, I need you to answer these 3 questions. How does acceleration change during free fall and why? How does velocity change during free fall and why? And how does distance traveled change during free fall and why? Come back when you're ready. Hopefully you wrote down that acceleration is not changing, and that's because gravity is a constant as you're on the planet. That's the acceleration of gravity, and it doesn't change on Earth. The next one, how does velocity change? Well, we were adding 10 every time because acceleration tells us to add a certain amount every second. And then the distance traveled got greater and greater and greater every single second, and that's because Bieber was going faster and faster and faster. The faster you go, the further you travel in a second. We need to add a little bit more to your notes about this topic. So acceleration has a direction too. So just like velocity had a direction and momentum had a direction, acceleration has a direction also. So let's cover that next. So I have on the screen the next note I want you to add to your notes side. And it says, if velocity and acceleration are going the same way, give them the same sign. If it's opposite, one is negative. So for example, if you have something that is falling down and you've decided to call that the positive direction, well, acceleration of gravity helps things to fall down. So it's going to be adding to that velocity. So if you call that way positive, your velocity and your acceleration are going to both be positive. Let me show you a picture like that. So in Bieber's case, he was going down because of the acceleration of gravity, and so his velocity was increasing. So both of those things are in the same direction, so we gave them the same sign. So throughout that whole practice question, everything was positive. However, think about if you're throwing something up in the air. At the very beginning, when something leaves your hands, when you throw it up into the air, It's got a velocity going up. And let's say we call that positive, because usually people think as a positive direction as up, but it really doesn't matter. But for this case, let's call it up, positive. Well, in that case, acceleration always points down of gravity. And so since they're opposite of each other, the acceleration would have to be negative. And hopefully that makes sense. As something is flying up into the air, it should be slowing down. Gravity is going to be slowing it down until it eventually hits the top of the arc at the very peak. So because velocity is positive and acceleration are negative, they have to have opposite signs. However, on the other side, when the thing starts coming back down, they're going to have the same sign as each other. And so in this case, because we called up positive at the very beginning, they'll both have negative. But notice, gravity didn't change. Gravity always points in the same direction. But your object can be having velocities in other directions. Let's do a practice problem with this idea. Over on your practice side, I want you to think about my puppy cannon. That's right, I have a puppy cannon. So if I have a puppy cannon, and all that you know about my puppy cannon is that the puppies come flying out at 40 meters per second, very fast velocity for a puppy especially, I want you to be thinking about the velocity and the acceleration as we travel through the puppy arc all these seconds later. So 1, 2, 3, and I didn't have enough space up here, but 4 is up there, and then 5, 6, 7, and 8 seconds through the whole trip. Please make a little sketch of this on your practice side. Pause if you need to. Now let's go through these parts together. So the only thing we're given is the starting velocity, 40 meters per second. Well, the acceleration of gravity is going to have to be a negative 10, because if we called the puppy coming out of the cannon a positive 40, puppy's going this way. Gravity always points down, so they have to have opposite signs from each other. So the acceleration of gravity is negative 10, and 1 second into the trip, the acceleration took away 10 from the velocity. So we started at 40, we went down to 30. Pause this video and see if you can fill in the rest on your own. Come back when you're ready to check. Okay, let's check. So hopefully you put for the next one that the acceleration is still negative 10. Now puppy has slowed down to 20. 3 seconds later, puppy has slowed down to 10, but gravity didn't change. And all the way up at the very tippy top, even though it doesn't have it up there, that's the moment that puppy stopped for just a split second where his velocity hit 0. Now acceleration and velocity are going to be working with each other. Now acceleration is still negative 10, but the velocity is negative 10 also, because puppy's going down now. And puppy's velocity is going to keep increasing in the negative direction until puppy eventually gets back down to where the cannon is at negative 40. So check that out. Puppy left the cannon at 40 and came back down at negative 40. And that's true for any object that you ever throw up into the air. If you remove air friction, which definitely is a component, but it's a little one, if you take some object and you throw it up into the air, it always comes back down, as long as you're at the same height, it comes back down at the same rate. So that's why, if you've ever heard this before, it's super dangerous to fire a gun up into the air, because that bullet leaves the gun at a really dangerous velocity. It also comes back down at a really dangerous velocity. So don't fire guns up into the air. I have 2 practice questions for you about this topic, and I need them over on your practice side. The first, I guess there are 2 practice scenarios. Here's the first scenario. It's about a ball. So you throw a ball straight up in the air. If the ball leaves your hand at a velocity of 20, I want to know how long is it going to take to reach the maximum height. I also want to know how long will it take to come back down, and how fast will it be going when it does. Then the second bullet is where I've added a little detail to see if you can work through this. What if somebody at the top, this girl right here, what if somebody at the top catches it and throws it back down instead of just letting gravity take hold, and that person throws it with 8? How fast will it be going if it's allowed to fall for 2 seconds after that? Pause this video and work those out on your practice side. Let's check and see how we did. So for the first one, 2 seconds to get to the top, 2 more to come back down, and it's going to be going 20 meters per second when it gets back down. For the second one, if the person starts the ball with 8 meters per second, gravity is going to add 10 to it every second. So it'll be going 28 after 2 seconds if it started with 8. Here's where we're at. We have now completed the second objective. Hopefully now you're able to determine the velocity and displacement for objects in a free fall using the equation that we've already been using for a change in velocity over change in time. The last thing that we need to do is do some free body diagrams and Newton's second law to talk about free fall. If you need to take another break, now is a good time. Get up, take a stretch, walk around, get a snack, take a little break, and then come back when you're ready for the last thing. In free fall, our free body diagrams are actually pretty simple because we only have an up and a down component. We're going to ignore anything from side to side. And the down part is always going to be weight. Not gravity, weight. And it's different for every skydiver. So if you are like me, I have a big weight. I would have a weight arrow pointing down that's much bigger than maybe yours would. The up direction is going to be air resistance. So just like you saw in the beginning of this video with the feathers and the bowling ball, the reason why the feathers fluttered down slowly is because air resistance pushed back against them and caused a counter force to their weight. Over on your notes side, for this third objective, I want you to make a sketch of a skydiver, and I want you to make these two notes so that you can remember what these two arrows are going to mean, because we're going to draw a bunch of these pictures for skydivers. Then over on your practice side, I need you to answer these three questions as kind of review. So the first one, what will the skydiver do when the forces are balanced? What will the skydiver do when the forces are unbalanced? And how does opening the parachute change this diagram? Pause the video and answer those three questions. Ready, go. Let's quickly review. So when a free body diagram is balanced, like the one that's on my screen, those are objects that are not going to accelerate. So if you are skydiving and your weight arrow is the same as your air resistance arrow, you're still going to be moving really fast. Your velocity isn't zero, but you're not going to be speeding up anymore. They call that terminal velocity, where your weight and your air resistance are the same. And that's where you're going, I think it's on Earth, and depending on the size of your body, something like 200 miles per hour. But those two arrows have canceled out. When those two arrows are unbalanced, that's when something's going to accelerate and start to speed up. When they pumped out all of the air from that air chamber where the bowling ball and the feathers were, they basically took out the top arrow, the air resistance. And so those objects were able to just free fall. The only thing left was weight. There was no air resistance. And so those things accelerated the whole time. And since they both experienced the same acceleration, gravity is the same acceleration for everything, they fell at the same rate. And then the last one, so opening the parachute makes that air resistance arrow much, much bigger. And if you're already falling and your arrow is bigger in the up direction, you'll start decelerating. But we'll get into that in just a second. In order to practice this, we're going to look at somebody named Felix Baumgartner, who you might have heard of from years past. He is this person who basically took a weather balloon to the very, very top of the atmosphere, the edges of space. You can see a picture right here. And he jumped out and then parachuted all the way back down to Earth. So he holds the record, I think still holds the record, for the highest altitude free fall for a human being, which sounds dangerous to me, but that was what he wanted to do. So what we're going to do is we're going to explore different parts of his free fall and draw free body diagrams to make sure that we understand how acceleration works. I need you to go into the Felix Baumgartner document that's in Google Classroom, and we're going to do the first one together, but then you're going to fill in the rest on your own. Let's go there now. Here's what the doc looks like. Up at the top, there is a link to go and watch the video. When you go to the link, you'll get to this site, and if you scroll down just a bit, this is the video right here. We'll come back to that in just a second. Your job is to do two things for a couple of different scenes from the video. So I've given you a timestamp. The first one that we're going to do together is at just 10 seconds into the video, and then you can see the timestamps for the others. The first box is where we need to write in the acceleration from gravity, Felix's altitude, how high up he is, and what his downward velocity is. Then we're going to draw the free body diagram. So let's do the first one together. So here we are at 10 seconds into the video. I've got it paused at 10 seconds. Let's take a little tour of some of the things that are going on because it's a very busy screen. So there were cameras that were mounted all over Felix's suit, and they also were recording a number of things using these gauges over on the side, and we've got some graphs. The things we mostly want to watch are these dials over here on the right. But it's also kind of cool to see what Felix sees. So at this 10-second mark, he is still close enough to Earth that he's experiencing Earth's gravity, so his acceleration is still going to be 10. Right now, his velocity, it says 4, and I think that's because the weather balloon that he had just stepped off of, it was actually technically falling just a little bit, but Felix himself, relative to the balloon at least, wasn't falling at all. And right now, his altitude is right here. We're going to go with the one in meters, where it's 38,969 meters. So he is way, way up there. Back over on the document, we're going to put in that his acceleration was 10, that his altitude was 38,000, and that his downward velocity, even though it said 4, we know that his velocity was actually 0. He had just stepped off. Now for the free body diagram. I always like to use a box to represent the object that we're talking about because I'm not a very good artist, and you can do the same if you'd like. Now we need to draw some arrows. So Felix has a weight that's pressing down, but at this point there is no air resistance. He is not experiencing any of the atmosphere yet, and he hasn't even started falling yet. But notice that this diagram is unbalanced, so that he is going to start accelerating. Your job is to go through the rest of these and fill in the boxes for each of the timestamps, and then I need you to check the answer key PDF at the very end when you're done. If you're still watching this, you've finished the Felix Baumgartner activity. Let's make sure that you've got everything ready to go to turn in this lesson. For the closure, I need you to take a picture of your practice page, which might be 2 pages. You did a lot of work today, and attach them to the assignment. Then make sure you click download in Kami on your Felix Baumgartner page with all the free body diagrams and attach it to the lesson, and then click turn in and you're done.